Okay, some notes about this solubility chart. Some of the values in the table will say SS, which stands for slightly soluble. For our purposes, that means we're going to classify them as insoluble. And like I said before, the table only works for ionic compounds. There's no molecular compounds listed. An acid falls into the category of molecular compounds, so you won't find it on the table, but acids, for this class anyway, are considered to be soluble. And then here's that table, 7.2 in the text. If you get a compound, you won't get any on the exam that aren't on that solubility chart. But if you get one on the homework, you can look at the flow chart in Chapter 7 to figure out whether it's going to dissolve or not. We're going to take this table of ionic compounds, and now we're going to look at chemical reactions. So when you mix together two ionic compounds, you may, which means you also may not, see evidence of a chemical reaction occurring between the two. And we can predict the products of this type of reaction, which is called a metathesis reaction. Or more commonly, it's called a double displacement reaction. So for example, the two chemicals that we looked at with the solubility table in the previous video, barium iodide and sodium sulfate. We know barium iodide, BaI2, and when we looked up the value in the table, barium iodide was aqueous, that was the 68. So when I write a chemical reaction, barium iodide, aqueous, I'm going to react that with sodium sulfate, and we looked up the value. Sodium sulfate was a 20, so that's also aqueous. I'm going to leave a line for my coefficients out in front. In order to figure out what products are going to be made, we're going to apply this double displacement technique, which means we switch the positive and negative pairs. We always know that the positive, the cation, is always written first in an ionic compound, and the anion is written second. So we know the sodium is always positive, sulfate's always negative. Double displacement means the positive part of the first chemical is going to switch, it's going to be attracted not to the other cation. Positive repels positive. So the positive barium is attracted to the negative sulfate. At the same time, the positive sodium is attracted to the negative iodide. So in order to figure out the products, what we're going to do is do another crisscross. We're going to take the barium and pair that up with the sulfate. So the most important part of this that most people miss, if they do, is they forget to do the crisscross. You have to go back to the periodic table and recognize barium, group 2, main group metal, always is a positive 2 cation. Sulfate, polyatomic anion with a negative 2 charge. So we do our crisscross, and we get a 2-to-2 ratio that can be simplified to a 1-to-1 ratio. So barium sulfate is one product of this double displacement reaction. The other combination is between the sodium and the iodide. Now remember, sodium is always a positive 1 cation, iodide negative 1 anion. So if we do our crisscross, we also get a 1-to-1 ratio. And then I leave parentheses to figure out the phase. Notice I did not include this 2 subscript on the sodium or this 2 subscript on the iodide because those are not part of the chemical formula. Sodium is just a positive 1 cation, and to make sodium sulfate we needed a 2-to-1 ratio between sodium and sulfate. When we do the crisscross, those subscripts were not included. However, the sulfate has a subscript of 4. Why did I include that subscript? It's because the 4 is part of the polyatomic, and remember, polyatomics stay together and act as one unit. So you cannot get rid of that 4 subscript the way we were getting rid of the 2 on the sodium and the iodide. Now for both of these, we have to fill in the phase by looking at the table in the lab manual. So barium sulfate, barium and sulfate is 2 times 10 to the negative 4th, which is less than 1. So barium sulfate does not dissolve in water. That would be solid. We do the same thing for sodium iodide. We find the sodium and iodide. That gives us a value of 64, which is greater than 1, so it does dissolve in water. So sodium iodide is aqueous. That gives us the phases, but we haven't balanced this reaction yet. So if I rewrite everything to make it look a little neater, I have barium iodide, aqueous, reacting with sodium sulfate, aqueous, and then on the product side I make barium sulfate solid and sodium iodide aqueous. Now I have all the reactants, all the products, but I need to change some coefficients. For example, I have 2 sodium on the left. I need 2 sodium on the right. That's going to balance my iodines. 2 on the right, 2 on the left. I have 1 barium, 1 barium, 1 sulfate, 1 sulfate. So this is my overall balance reaction with all of the proper phases and the correct coefficients. The last thing to notice is we made a solid product, and the fancy term for the solid that's made from reacting 2 aqueous solutions together is a precipitate. So this is a double displacement reaction that makes a precipitate, and the precipitate is barium sulfate.